Okay, let's talk about hybridization theory. If we were to draw a methane molecule out, okay, with 4 bond pairs, we know that according to Vesper, this is going to have a tetrahedral shape. Okay, if we were to look at carbon, carbon has 6 valence electrons with a configuration of 1s2, 2s2, and 2p2. Let's draw the energy level diagram, right? So we have 1s, 2s, and the 2p orbitals. Okay, 2 electrons here, 2 here, and 1 each here. Okay, let's try to sketch out what the current orbitals look like, right? X, Y, and Z. So we have our S, our 2p orbitals as well. Okay, and we know that we're going to have 2 electrons in our S and 1 in our p orbitals each. Okay, trying to draw a nice overlap to form a tetrahedral shape is going to be impossible, right? Because we know sigma bonds have to be formed via head-on overlap, right? So no matter how you draw it, you will never be able to get a nice uniform tetrahedral shape using our current orbitals. So hybridization theory is a theory created to explain why methane has a certain shape or why other molecules have certain shapes. Okay, so the theory is that atomic orbitals can actually combine to form something called a hybrid orbital. Our first step is always to determine what kind of hybridization is present in my molecule, right? So if you look at carbon here, we know that carbon has 4 bond pairs. If it has 4 bond pairs, it means that it has sp3 hybridization. Because the s has an invisible 1, so 1 plus 3 will give me 4 bond pairs. Okay, that's an easy way for us to remember what kind of hybridization it is. Okay, so I'm going to label here. Our first step, carbon is sp3 hybridized. Our second step now is to know that this means that one s orbital will combine with 3 p orbitals to give us 4 sp hybrid orbitals. Okay, this sp hybrid orbital has a drumstick shape, okay, compared to the spherical shape of our s orbital and the dumbbell shape of our p orbitals. And if we were to look at our energy level, what is happening here is that these orbitals will now combine to form 4 degenerate sp orbitals. Okay, degenerate. Degenerate means same energy level. Okay, it's going to be in between 2s and 2p's energy levels. Okay, where we're going to have 1, 2, 3, 4. 1 electron in each of these sp hybrid orbitals. Our third step now is to arrange them in the shape. Right, we know that we have a tetrahedral shape about this carbon atom, so I'm going to arrange my sp hybrid orbitals in a tetrahedral shape. So there's one. Oh, draw it a little bit nicer. Okay, make sure to always start off in the intersection here, okay, to make your diagram look nicer. So there's 1, 2, 3, and 4. So this is my central carbon atom, right? Now it looks a lot more tetrahedrally, right? Okay, next is to draw our overlap with our H. So I'm going to use blue here to represent H. So we have 1, 2, 3, 4, right? And we are going to have 4 head-on overlaps here, which will form 4 sigma bonds. So because of hybridization, okay, this lets us explain why methane here has a tetrahedral shape. Okay, let's apply these same steps for another molecule. Let's look at ethene, for example. This is what ethene looks like. Okay, step 1 is to identify our type of hybridization. So here we have 3 bond pairs about this carbon. So we know that it's going to be sp2 hybridized, right? And this carbon is going to be sp2 hybridized as well, which means one s orbital combines with 2 p orbitals to form 3 hybrid sp orbitals now. Okay, so let's start with this carbon. Okay, we know that 3 bond pairs means that it's going to have a trigonal planar shape. So I'm going to draw my hybrid orbitals in a trigonal planar shape. 1, 2, 3. This is my carbon. And we also need to draw for this carbon as well. Okay, so we're gonna draw 1. Let's make it a bit nicer. 2, 3. This is my second carbon. Okay, so similar to just now, I am going to draw my H as well. And again, 1, 2, 3, 4, 5 head-on overlaps, right? Which form our 5 sigma bonds. So sigma bond, sigma bond, sigma bond, sigma bond, sigma bond. Okay, but for ethene, we are going to have this pi bond here as well. Okay, in the hybridization process, we used up 2 of our p orbitals, which means we are going to have this, a third orbital that was unhybridized. Right? So let's just draw the unhybridized p orbital over here. Okay, so this is actually a side-on overlap, which will form us a pi bond. Okay, because you are taught that a side-on overlap looks like this. Agree? And so this is the same thing, right? They're just, it looks slightly different for clarity's sake. All right, so last example is of course going to be our triple bond. So let's just draw an ethyne molecule. So we're going to take it a little bit faster now. We know that this has 2 bond pairs, so it's going to be sp hybridized. Okay, and 2 bond pairs means it's going to have a linear shape about carbon. So let's draw our sp hybrid orbitals in a linear shape here. Carbon, carbon. Okay, and we know we're going to have 2H or 2H atoms here to form our sigma bonds. So sigma bond, sigma bond, sigma bond. Okay, and in ethyne, this triple bond here, it means that we have 1 pi and 2 pi bonds. Okay, we have a total of 2 pi bonds. So in this case, we're going to have 2 p orbitals that are unhybridized. So let's just draw one of them first. Right, this again is going to be a side-on overlap which forms a pi bond. And our second one has to be perpendicular to our first p orbital. So we're going to draw it like this to show that they are perpendicular. And this here represents our second pi bond. So with that, okay, just to take a look at everything again, this is our ethyne molecule, okay, which now our diagram corresponds very well with the shape. Same thing for ethyne here, and our first example of methane. Okay, with that, that's all I have for hybridization theory. Hope this helps clear up any misconceptions you may have. And yeah, that's all. Thanks for watching, and let me know what I should cover next. Bye bye.